Hello, in this video, we will first learn graphical representation of motion and then end this chapter on motion with uniform circular motion. First amongst graphical representation of motion is the distance time graph. Here are two examples of distance time graph. The first example here is an example of constant velocity. So how do we find it is a constant velocity? Velocity is given by the slope of the graph. We can clearly see here that the slope of graph is constant. And how do we find out the slope of graph? It is found out by the distance BC divided by the distance AC. Now we can also find velocity in the second graph. In the second graph, the velocity is found out by finding slopes at different times. So here we see that velocity is continuously changing as the slope of this graph is continuously changing, and in fact it is continuously increasing. Hence the velocity is also continuously increasing. Now we come on to velocity time graphs. In velocity time graphs we can have three different type of graphs. The first one here is the constant velocity graph. The second is a velocity which is constantly increasing, and the third is a velocity which is increasing and then decreasing and then increasing, that is, it is not constant and has different accelerations at different intervals of time. So what information can we find out from velocity time graphs? The first information that you can find out from velocity time graphs is that if this velocity is constant or changing with respect to time. So in this first example, the velocity is constant. The second example, it is continuously increasing with a constant acceleration. And in the third example, it is variable with different accelerations at different intervals of time. The second information that you can find out is the displacement or the distance traveled during the time interval, say t1 to t2. To find out the distance traveled, what we have to do is we have to calculate the area that is enclosed within this time interval t1 and t2, and just that will be equal to the distance traveled. So suppose in the first example, the distance traveled here, I'll write distance traveled is the area under this graph, that is area of ABCD, or also this blue shaded region. Now, in order to find the distance traveled in the second example, the second graph, we need to find the area AECB, that is the area under the curve. Now this figure is also called a trapezium. To find the area of trapezium AECB, we can divide it into two parts, that is triangle AED and a square or rectangle, say ADCB. So if we write here, the distance traveled in this case will be equal to area AED plus area ADCB. So this, which is equal to the whole shaded region in blue color. Now in the third example, if we need to find out the total distance traveled, we can divide it into time intervals, say t1, t2, t3 and t4. Now what we can do is we can individually calculate the area for this region 1, region number 2, region number 3 and region number 4, the same way we did it for the second case, and then add all these things and we'll get the total distance traveled. Now the third information that we get from velocity time graphs is the acceleration. Acceleration is slope of velocity time graph, VT graph. So the first case, the slope is 0, hence acceleration is 0. In the second case, we see that acceleration is constant, with a constant, and the slope in this graph is positive, therefore the acceleration is positive. In the third case, we see that in the region 1, the acceleration is positive. In the region 2, acceleration is negative. In region 3, it is positive again. And region 4, it is negative. So, this is what our all velocity time graphs can give us information about. Now, we will look into the equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during the motion, and the distance covered by it in a certain time interval by a set of equations known as the equations of motion. These are: the first one is v equals to u plus at, second is v square minus u square equals to 2as, and the third is s equals to ut plus half at square, where v is final velocity, u is initial velocity, s is the distance traveled, and t is the time taken for this distance to travel, and a is the acceleration during this time interval. Let's move on to the last topic of this chapter, that is uniform circular motion. We know that acceleration is equal to change in velocity. Velocity itself has two components, with magnitude and direction. Change in either magnitude or direction causes acceleration. So we have to keep in mind that whenever we are talking about velocity or we are talking about acceleration, we need to think about magnitude and as well as its direction. Now consider following figures. The first figure here shows a rectangular track. Now suppose an athlete starts from point A and goes along this rectangular track ABCD and comes back along to the point A. Now when he starts running from point A to point B, there is no change in direction. Also, we are assuming here that the magnitude of his running speed is same throughout. Now, as soon as he reaches the point B, there is a sudden change in direction of his motion. So we say he has an acceleration at point B. Now again when he reaches point C, there is an acceleration because his direction again changes suddenly. And similarly, at point D, he has an acceleration because again he changes his direction. So in total, he has to change his directions 4 times in order to complete the full track. Now, we take an example of the second figure, that is a hexagon. Here, he has to change his velocity 6 times in order to be on the track. Now, as soon as we increase the number of sides to 8, we see that he has to change his velocity 8 times during his motion in order to be on the track. Now, let's consider a track which is circular in shape. We see that the velocity of the athlete changes at every point of the circle because he is changing his direction at every point of the circle. Hence, he has an acceleration during the motion. Now, for a circle, circumference is equal to 2 pi r, where r is the radius of the circle. If the athlete takes t time to complete one round, his speed will be the distance traveled, that is 2 pi r, upon time taken, that is t. When a motion along a circular path is done with uniform speed, it is called uniform circular motion. That is, motion of satellite in a circular orbit around Earth or motion of moon around Earth. Now let us look at a fun activity. What we do is, we swirl a stone tied at an end of a string holding the other end. Now, as soon as we leave the string, the stone moves in the tangential direction. And it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changed at every point when the stone was moving along the circular path. Suppose we are swirling the stone along this circular path, with stone being here and it is tied to the thread and the man standing at the center. What we see is, as soon as the thread is cut at this point, the stone goes in this direction. Now, if the stone is at this position and the thread is cut at this instant, we find that the stone moves in this direction. Hence, we see that every time the thread is cut, the stone moves in a particular direction, that is the tangential direction along the curve. Now, what we find from this is that the direction of motion is continuously changing along the path. Now, even if the magnitude of the speed during the motion is constant, we see it has an acceleration. Hence, we see that even uniform circular motion is an accelerated motion. Uniform circular motion is an accelerated motion. With this, we end the chapter on motion. Thank you.